What we have looked at so far are three examples, special examples of first order differential equations. X dot equal to Rx minus x squared, which has the fixed points x star equal to 0 and R. This is stable if R is less than 0, and this is unstable for R less than 0, and then this is unstable if R greater than 0, and this is stable for R greater than 0. So there is exchange of stabilities at this point x equal to 0. So if I make a plot of the fixed point versus R, at R equal to 0, x star equal to 0, there is an exchange of stabilities. This was stable for R less than 0, and this becomes stable for R greater than 0. This is what we called a bifurcation, and this particular bifurcation was termed transcritical bifurcation. So x dot equal to Rx minus x squared. The next thing which we encountered was x dot equal to Rx minus x cubed, which has the fixed points x star equal to 0 and plus minus square root of R. So this exists only for R positive. This one is stable for R less than 0, unstable for R greater than 0, and this exists for R greater than 0. Both of these exist for R greater than 0, and both of them are stable for R greater than 0, giving rise to the picture that x star versus R looks like this, where the other fixed points living on this parabola over here, and this is stable, this is stable, this is stable. So there is a bifurcation again over here at x star equal to 0, R equal to 0, because of the picture suggests the name, the Pitchfork bifurcation. And then we encountered, did a third, which was x dot equal to r minus x squared, where the fixed points are x star equal to plus minus square root of r for r greater than 0. No real fixed point for r less than 0. And what the question was about is that there is a fixed point at x star equal to 0 for r equal to 0. So there is something to be said about that. So x star equal to plus minus square root of r for r greater than 0. No real fixed point for r less than 0. Obviously, if x star r is equal to 0, there is a double fixed point, actually two of them coalescing. So it's x equal to 0. The picture, remember, was this, that here is r once again, and that's my x star. There is this parabola over here, and the positive branch is the stable one, and that's the unstable one. So this is what one calls tangent bifurcation. The line r equal to 0 becomes tangent to this fixed point curve over here at x star equal to 0. That's why one calls it a tangent bifurcation. The bifurcation is in the sense that you are moving from a region which has two fixed points, a stable and an unstable one. As r is taken from positive to negative values, these two fixed points, the two fixed points for r greater than 0, come and merge at this point and thereafter coalesce and disappear. So there is a point at which they merge, which is the merge at r equal to 0. So there is r equal to 0 is x star equal to 0 at r equal to 0 is a fixed point, and if you look at what this fixed point is about, so this is the origin. So x star equal to, at this point, x dot is equal to minus x squared. Linear stability analysis would not tell you anything about the stability of this x equal to 0, but just by looking at it, x dot equal to minus x squared, should I start anywhere on the on this side over here, the negative x dot would mean that I would get closer and closer to the origin. So the flow would be towards the origin over here, and I would end up over here. But suppose I start on this other side over here, it's x dot equal to minus x squared once again. X dot remains negative, so if you should start out over here, then you just flow away. So it will take you an infinite time to cross the origin, effectively meaning that, this flow stops over here for all practical purposes if you are starting out on this side, and if you start out, if it takes a long time to get out on. It's this, crossing the origin is not on the cards. X dot equal to minus x squared, which integrates out to dx over minus x squared equal to dt. So 1 over x minus 1 over x naught, wherever you start out, if t equal to 0 is the starting point, x equal to x naught. So that if you start out at your x naught somewhere or other, it's this 1 over x minus 1 over x naught, x going to plus infinity. So x going, if you start out from this side over here, then you will reach x equal to minus infinity at the time. So if x naught is negative, if x naught is negative, then it is you are going to reach your negative infinity at a finite time, which is given by t equal to 1 over x naught. So start over here, you'll run over to infinity in a finite time. Start on this side over here, you are going to hit x equal to 0. Wherever you start out with x naught on the positive side, you are going to reach x equal to 0 at an infinite time. So it takes you an infinite while to start out from here and reach the origin. If you start out over here, it takes a finite time to hit minus infinity. Difference in behavior on the two sides over here. This point doesn't look like the ones that we have talked about, fixed points we have talked about so far, in the sense that fixed points that we have talked about are either stable or unstable. That if it's a stable fixed point, then disturb it, change the starting out point a little bit. It's going to flow in towards the fixed point. Unstable, start it out somewhere away from the fixed point. It's going to flow out. So that's the unstable fixed point. There is the stable fixed point. If you look at this one over here, it is somewhat different, neither stable nor unstable. Not surprisingly, all these were determined by linear stability analysis. This one, linear stability analysis fails. If you, on the other hand, you can integrate it out and see what happens, and what happens is that what I've just described. So on one side, if you look at it on this side, you would be led to believe that it's a stable fixed point. Look at it at this side, you are led to believe that it's an unstable fixed point. Hence, if you want, you can use the terminology semi-stable, which is what Strogatz uses, but fine. I mean, that's what the meaning of, to answer the question, that's what the meaning of semi-stable is under these circumstances. Linear stability analysis does not give any answer for you. So all these cases where it is semi-stable are cases where linear stability analysis fails, and but even if linear stability analysis fails, you can analyze what is going to happen, and if you are lucky enough to be able to integrate it out easily. And this one is a particularly easy example, and you can see what happens. So, as these fixed points move in, and as you lower the value of r, they coalesce. X at r equal to 0, x equal to 0 is still a fixed point, and thereafter they disappear. So that's the tangent bifurcation, which was the third thing that we talked about. So, so these were the three bifurcations which people generally talk about, and the next question that I want to take up is, is there a characteristic difference between these three situations? Is what happens to the bifurcation? So long we have been talking about what happens to a fixed point if I change the, if I start out. If you start at the fixed point and try to integrate the differential equation, you just remain where you are. If you shift it slightly and start integrating, you either move towards the fixed point or away from it. Stable, unstable, determined by that. But what we ask now the question, what happens to the bifurcation itself? So it's the question of what happens to the bifurcation if I add if I add an imperfection. So adding an imperfection means I just add a little bit of constant term, x dot equal to Rx minus x squared plus some epsilon, x dot equal to Rx minus x cubed plus epsilon, x dot equal to R minus x squared plus epsilon. So I'm going to add a little bit, just perturb the form of the differential equation by adding a small constant term and see what effect it has on the three different bifurcations. So, all right. So x dot equal to Rx. You see, there is a common theme between the first two, which we talked about a bit at the end of the last lecture, that in both of these, in the absence of epsilon, x equal to 0 is a fixed point of both these equations. And it's a trivial fixed point in the sense that x equal to 0, that's x equal to 0, x dot is equal to 0 for x equal to 0, it's identically 0. So, whereas, I mean, x equal to 0 is not a fixed point for x dot, so this is going to have a repercussion when I add a small epsilon to what I have. So, x dot equal to Rx minus x squared plus epsilon. Now, the fixed points, I have to look at the fixed points of it. Fixed points come from R x star squared minus Rx star minus epsilon equal to 0. So, x star is going to be R plus minus square root of R squared plus 4 epsilon divided by 2. So epsilon equal to 0, R and 0, and now I have a little bit of epsilon over here. So if I have a little bit of epsilon over here, and I'm looking at the negative fixed point, the negative sign over here, so now plotting x star versus R, and at R equal to epsilon positive, I have, let's assume that epsilon is positive for all these cases. Now R equal to 0, if I set R equal to 0, x star is equal to square root of plus minus square root of epsilon. So at R equal to 0, that's at this point over here, I have two options, x star is plus epsilon or minus epsilon. So the two fixed points at R equal to 0 coming together, and x star equal to 0 coming meeting x star equal to R, that feature is already lost. So that's the problem of having the origin as a trivial fixed point, that as soon as I add a constant over here, the origin is no longer a fixed point. And fine, so it's not a fixed point. Then what? What about, so let's follow the R equal to 0. So it is going to be the one which was R equal to 0 is the one which is R minus square root of R squared plus 4 epsilon by 2. What happens if R becomes extremely big? If R becomes extremely big, it has to go to 0. So asymptotically it goes to 0 on this side over here. But what about R becoming extremely large and negative? Is if R becomes extremely large, look like this. So the fixed point with the negative sign looks like that. And what about the fixed point with the positive sign? The fixed point with the positive sign over here. So looking at the fixed point with the positive sign, it goes off to R as R goes to so that asymptotes to x star equal to R and goes to 0 as R becomes negative. So this is what they look like. And the picture is very different from the exchange of stabilities which you had over there. So x star equal to 0. So look at the stability of these fixed points. So I'm looking at the stabilities over here. If you are looking at this x star, you want to look at f of x star. F of x star is going to be R minus 2x star over here. So R minus 2x star is going to be, so it is R minus R, and you are going to have minus over here, so minus plus square root of R squared plus 4 epsilon. So if I'm going to look at the plus sign over here, this plus sign over here is going to give me the negative sign over here. So that is going to be stable. So you have a stable fixed point over here for epsilon positive, and this always remains stable. Minus, so this over here, the minus sign is giving you this, and there is this question, this remains stable, this remains unstable. So you don't have the entire issue of the bifurcation is lost. You still, should you start on this somewhere between this point, say I am at this value of R, and if I start my initial condition somewhere between here and over here, or from the other side, I would indeed hit the hit this curve over here. You will land up at this point just as you would have landed up at the upper curve over there, if wherever you started out. Well, the difference is that if you started out over here, you would not, and over there, there is the unstable fixed point, which is that R equal to 0. So everything for initial conditions, all negative initial conditions would run out to infinity. Over here, all initial conditions which start from over here are going to go out to minus infinity. But if you start out anywhere between this line and this plus infinity, you are going to end up on this branch over here, which is the same branch as this. So there is no changeover from one branch to another. Qualitatively, it may still seem that, all right, I mean, you were ending up on at x star equal to 0 for negative values of R. Well, over here you will be ending up with some small value of x star if you are on this negative side over here, and you will be ending up with some final larger value of x star if you are R equal to R positive. But there is no question of transferring stability from one branch to the other. So the bifurcation is gone. So no question of bifurcation over here. So you have put in an infinitesimal amount of epsilon, and the question of bifurcation is no longer there. Bifurcation was that when I move from one solution to another solution, Here there are two solutions, all right, but I never move from one solution to the other. So no question of bifurcation over here. That so-called transcritical bifurcation is actually wiped out by this infinitesimal perturbation. All right, so the next is the pitchfork. The pitchfork is more interesting, also because this equation is actually of physical interest. It's x star equal to Rx minus x cubed plus epsilon. Now, when I talked about the epsilon equal to 0 case, I said that this particular chap, x star equal to Rx minus x cubed, is of interest because it does model at a mean field level a variety of physical systems, in particular those with the second order phase transitions, say a picture of magnetization in the mean field magnetization transition from paramagnet to ferromagnet in the mean field picture. So in the mean field picture, this is like m dot equal to am minus bm cubed. The mean field free energy for the transition is am squared by 2 plus bm4 by 4, and having this change for A positive, A is proportional to T minus Tc, and for A positive, the free energy looks like this, whereas for A negative, it looks like this. And so it is a transition as A goes from positive to negative. You go from a paramagnetic state to a ferromagnetic state. So this is what, and the dynamics, why is the dynamics this? As I said that if you are looking at the static properties of this magnetization, the dynamics which would lead you to the correct free energy in the infinite time limit, so get the statics right out of a dynamics, would be at first order dynamics which would look like this plus some noise term. So you are looking at, so m dot equal to am minus bm cubed mimics the regular part of the dynamics of the magnetization. There is, as I said, in reality there would be a noise term coming from the small wavelength fluctuations, which would ensure that equilibrium distribution is indeed obtained with that f over there. And so on and so forth, but this is repeating that because what's important is that when I look at this one over here, it's like adding, all this is happening at 0. One talks about the transition in a 0 external field. That's when the fact that you have generated some non-zero magnetization is a spontaneous magnetization which has been generated, but add in a little bit of magnetic field. So if I have an external magnetic field, this free energy would have an additional term which is minus mh, and you are going to look at this question of having h over here. So additional h sitting over here. So additional additional, this is a greater than 0. This is a yes. So an additional h sitting over there in the equation of motion is like having an external field which couples to the magnetization, couples to a term which is m times h. So the perturbation that we are talking about over here, x dot equal to Rx minus x cubed, the Pitchfork bifurcation, having a perturbation bit added to it, this epsilon, is more interesting in some sense than the other case we dealt with, transcritical suffering perturbation, because this actually relates to a physical situation which is in the magnetic transition. I have put in an external, so the zero field transition has been made murky by an additional little bit of external field. So that's why it pays to look at this with little care. And see what happens. So once again, back to finding fixed points. X star minus Rx. I'll stick to epsilon. Well, alright, whether epsilon plus or minus, we'll talk about that. Let's start with epsilon positive. Then, so X star cubed minus Rx. Very good. Alright, so I have to cube. I have to find the fixed points over here. Let's say, to begin with, I don't know how to solve a cubic. This cubic is trivial to solve, but we'll get to that in a minute. But suppose I don't know how to solve a cubic. What would I do? I would just try to do it pictorially. So I'm looking for a solution of y cubed minus ry equal to epsilon. So if it is r greater than 0, let's start with r less than 0. If it is r less than 0, then it is this plot. So I'm plotting y cubed minus ry. Sorry. So I'm plotting this y cubed minus ry against y, and for r less than 0. So for r less than 0, it is y cubed plus something else, which so it is like y cubed plus some constant, positive constant into y. So y greater than 0, it is the sign is always positive. Y less than 0, the sign is always negative. So it's a linear behavior near the origin. This dominates near the origin. It's minus ry, but r is negative, so it's a positive slope going through the origin, and then y cube takes over, goes off like this. Y cube takes over, goes down like this. There's non-smooth nature of my drawing that, I mean, sort of, you know, sort of looks linear and then matrix, all pretty smooth. So that's what it is. And then epsilon, a constant. So epsilon, if positive, sits over here. Epsilon, if negative, sits over here. Either way, there is just one intersection. Right? So if r is negative, I have only one root, which is determined by this intersection point over here. So the So r negative, I have just one root root which is determined for epsilon greater than 0, the root sits over here, and at epsilon equal to 0, the root is at x equal to 0. So only one root at for this one over here at r equal to 0, it is going to be this question of either the r equal to 0, you are going to have slightly, there is this x cubed over here at, I'm looking at this picture, so you are going to see as this epsilon, there is going to be some root for finite epsilon, there is going to lower the value of epsilon, you are going to get the root comes closer and closer to 0, and then at x equal to 0, and the root goes to 0. If r equal to 0, you can easily see this happen. At r equal to 0, it is just epsilon to the power 1/3, and as epsilon goes to 0, it goes to 0, and it becomes bigger as epsilon becomes bigger. So that's what is happening with negative r, some amount of negative r as well. Nothing much going on, except that for it is a non-zero value of, so I try to draw, here is r and here is x star. I know that at r equal to 0, it comes to epsilon, for positive epsilon, it comes to epsilon to the power 1/3 for positive epsilon, and thereafter there is just one root, and must be looking something like this, which, I mean, as you make your r more and more negative, you can see this line over here tilt further up, and so this intersection is going to happen closer and closer to y equal to 0, so eventually this x star would go to 0. So you make the r more and more negative. This straight line bit over here would sort of get more and more steep, and so you would be heading towards y equal to 0, which is x star equal to 0. So this branch indeed looks like this up to this point over here. Fun starts when r is greater than 0. So r greater than 0. Now I have to look at this y cubed minus ry, but the linear part is now with a negative slope, and hence looks like this. So that's what the linear part looks like. And then there is this y cube to worry about. The y cube is a plus part on this side, so it will take this going down part of linear. Y cube is and this is how you go. So that's what this curve is going to look like. So this is what f of y, so f of y versus y for r greater than 0 has this look over here. And now it's interesting because if epsilon, now I have to draw the line epsilon equal to constant. So if I draw the line epsilon equal to constant, if epsilon sits over here, then as before I have only one intersection. But if epsilon lies over here, if epsilon is small enough, negative epsilon, the same statement. If epsilon is negative, if it is large and negative, only one intersection. But now make epsilon small enough. Small enough, how small? Now it has to be smaller than this value over here. Right? So if epsilon is smaller than this value over here, then I'm going to have three intersections. So there are going to be three fixed points. So R positive and epsilon less than, so my R greater than 0 and epsilon less than a critical epsilon, there are going to be three fixed points. So I should have three fixed points for epsilon less than some critical value. So what is this critical value? The critical value of epsilon is the value of f of y at this turning point over here. So f of y at this point has a zero derivative. So zero derivative, I want to find epsilon critical. So I find the f prime y equal to 0 is equal to 3y squared minus r. So that's the condition that y squared is equal to r by 3. That's the condition for having that maximum over there. So it is at y equal to minus square root of this if epsilon is greater than 0. So I have to evaluate this quantity f of y at y equal to minus this, and so it is f of y is going to be minus r into the negative root of this. So it is r times square root of r divided by square root of 3, and then it is minus r over 3 into square root of r over 3, which is 2/3 r square root of r over 3. So 2 by 9, there is square root of r. So it is 2 by 3 root 3 r to the power 3 by 2. So for any given r, so any given r which is positive, there exists epsilon critical. So epsilon critical equals 2 by 3 root 3 r to the power 3 by 2. For epsilon less than this critical value, r positive, I have three fixed points. But if r is greater than, if epsilon is greater than this epsilon c, if you are sitting with a high value of epsilon, then once again you are down. So alright, so I have to plot these fixed points over here. I note that if I think of r epsilon plane, if I think of r epsilon plane, then for r negative, for r less than 0, I always have one fixed point. So everywhere over here, I have one fixed point for r less than, in this region, which is r less than 0. if epsilon is positive and greater than this value epsilon c, this epsilon c equal to r to the power 3 by 2 defines a curve in the r epsilon plane. So it is epsilon equal to r to the power 3 by 2. So it goes off for positive epsilon like this, and for negative epsilon goes like this. So here is this curve which is epsilon equal to 2 by 3 root 3 r to the power 3 halves, and here is minus 2 divided by 3 r to the power 3 halves. If epsilon is greater than that value, critical value over there, then you still have one fixed point. Over here, it's one fixed point. Out in this zone over here, you have three fixed points. So there are three fixed points in this range over here. In this two-parameter problem, epsilon r, you can draw the plane where you can draw the r epsilon plane and see how the bifurcation picture changes if you change the values of epsilon and r. This kind of a picture, when you have several control parameters to play around, is often called a bifurcation diagram. It's a loose word. Many things come under this sort of general term of bifurcation diagram, but what very often you will find people mean is that your original system has several control parameters, and you are looking at the distribution of fixed points in the control parameter space. So over here I have two controls, epsilon and r. So it's a plane. The control parameters define a plane, and in this plane I have this these different regions. One essentially with two regions essentially, three fixed points and one fixed point. All right, coming back, now I need to complete the picture over here. So it's x star versus r for epsilon. So let's say this is for epsilon greater than 0.
Sir, epsilon equal to 2 by 3 root 3 or 3 by 2. We cannot say about 6 points of stability, right? In that point a prime.
Exactly on these two of these fixed points would disappear. I mean, exactly on the boundary, you would just have one fixed point, and two of them will disappear, just as they did over here with the with epsilon equal to 0. When I have this picture that this is for r versus x star over here. So there are three fixed points over here going over into one fixed point over here. On this at this point over here, the three fixed points sort of merge and become one fixed point. This was for epsilon equal to 0. Now that is what is going to happen on each of on this boundary and this boundary over here. The three fixed points would come and merge, and then only one fixed point will survive on those. Alright, so I need to now complete this picture for an epsilon greater than 0. So for r negative, I have the question of only one fixed point, and there is, I mean, you come and stay over, hit that. point at r equal to 0. Now I want to continue beyond r equal to 0, and what are the I have to now see that for r greater than 0, epsilon less than this particular value. So if it is epsilon less than epsilon critical, I should be having three fixed points. So all right, so you look at these fixed points over here. So here is r greater than 0. I have got these three fixed points over here, and those, if you are going to, let's say, worry about what the, it makes life easier if I going to see is that two of these fixed points, so two of these fixed points sort of emerge, are close to each other, having emerged from this maximum over here, when epsilon is, this is the point where epsilon is equal to 2 by 3 root 3 r to the power 3 by 2. So these are the two chaps who have sort of emerged from there, and they are going to be close to this point over here. So these two negative values of y, so two intersections at these negative values of y would be sort of close to each other, and then there would be a positive fixed point which is sort of independent of the events that are happening over here, which tells you the following, that this fixed point over here is simply going to continue and go over like this, but then there is at for epsilon which is smaller than I have fixed my epsilon at less than epsilon c, and so there is now r which is equal to r to the power 3 by 2. My epsilon is fixed at epsilon less than epsilon c. There is r critical rc 3 by 2, which is equal to 3 root 3 by 2 times epsilon. So this is going to be this rc equal to 3 root 3 over 2 times epsilon, which is going to be some value over here, at which point I am going to see the emergence of two other fixed points. So at this r over here, so for r greater than, for a given epsilon, this is a given epsilon greater than 0 diagram. So for given epsilon greater, smaller than the epsilon critical, there is going to be an r at which these two fixed points are going to emerge. That r for a given fixed is given by, given epsilon is given by this. So for r greater than that particular value, and you are going to see a couple of fixed points. So if you are exactly at r equal to if you are exactly at this point over here, which is are which will have to come to the, it's a question of what do these fixed points look like. Both of them are in the negative y part, as you can see from there. So they are going to be negative x star. So it has to be some value over here from which you are going to see the emergence of two fixed points which are going to go like this. So that's what the picture has to be, that these are the two fixed points which have to be for negative values of y, which tells you negative values of x star. They have to emerge from a point which is some finite distance away from this origin over here, and they will have to go to, obviously, as r becomes very big, epsilon becomes irrelevant, and you should just correcting the slope of that graph. So as r becomes very big, epsilon becomes irrelevant, and the x star equal to 0 fixed point should emerge, and this is what it's doing, emerging. This one should merge to 0, and this one over here should merge with the standard diagram for Pitchfork bifurcation. This is what we have normally, that Pitchfork looks like this over here. So that's my standard Pitchfork, x star versus r at epsilon equal to 0. Epsilon finite and greater than 0, what you have is that here is this chap over here going like this, and here is these two branches appear over here. So if you are far away, r large and negative, it is going to be one fixed point that you see over here. R large and positive, it is going to be three fixed points, this, and this, and which is exactly what you have over here, this, and this. So when epsilon becomes irrelevant at large values of r, you get back this picture over here, but in between there is a huge change when you try and draw the stability business. So, question, what about the stability of these curves? Which is this stable or unstable? Stable. So this is going to be stable. The stability, once again, picked up by the derivative over here. So it's going to be, this is going to be your stable, and this is going to be unstable, and this is stable back again. So stable back again. So it's S, Q, and S over here. And what has happened is that the bifurcation is once again lost. The bifurcation is lost because over here we had once again a stability which changed from one curve to another. There were these two bifurcation curves, x star equal to the solution curves, x star equal to plus minus square root of r, and x star equal to 0, and the stability passed from one curve to the other. Over here, the stability does not pass from one curve to the other. So you remain on this curve over here, always remain stable, and there is at some point a generation at some critical value of r. This is generated over this business is generated over here, and you are going to sort of see that there is this question of a different stable fixed point where you can land up if you start with initial conditions which are beyond this over here. Over here you landed up because of the symmetry that you had, plus minus symmetry that you had, all negative negative initial conditions took you to this curve, all positive initial conditions took you over here. There is, over here, it's not, the initial conditions have to be finite and negative. Finite, that is beyond this point, we are going to land up over here, otherwise you land up over there. So there would be initial conditions which will take you to this point over here, and there is that's it. But the bifurcation character, which meant that stability would pass from here to this set of curves over here. The change from one solution curve to another solution curve, that simply does not happen. The bifurcation as such is completely destroyed by the introduction of an infinitesimal perturbation. So, like the transcritical thing, there is this question of not being able to get the bifurcation going for a finite value of epsilon. The stable curve always remains a stable curve no matter what. So this is always going to remain a stable branch. Now, what happens is that, is a possibility is that there is going to be the emergence of this new fixed point at a certain critical value, non-zero critical value of R. Over here, there is a question of this negative thing emerging. So you can think of this, that if you were, alright, suppose you start from this end, you start from negative values of R and start making R closer and closer to 0. So you have started from above the critical point and you are making the temperature come closer and closer to the critical point. You can go through it without feeling anything. That is, there is a continuous, this curve over here was simply continuously changing, the magnetization continuously changes along this path over here. And if I were to, on the other hand, try to access this curve over here, then I would have to switch initial conditions to be lying somewhere in this region. So somewhere along this line, or somewhere below, if I put my initial conditions, then you would be looking at this fixed, this magnetization curve, and let's imagine that I have started out with a magnetization, a finite magnetization, and I happen to be on this curve over here. So I start out from here, from negative values, so high above the critical point, cross the critical point, stay on that curve, and nothing seems to be happening. I start out from this point over here. I start out from below the critical point, and let's say I'm starting out on this curve over here. So you start out from this curve over here, come to this point which is not R equal to 0. You come to this point and you suddenly find that this is lost. So if I were to come over here, suddenly, then you are on it, there is a finite jump in the magnetization, and you change from this point curve over here to this curve over here, and then as you raise the temperature some more, you go down to 0. So there is a jump in the magnetization. If I were to start out from over here and try to raise the temperature, then if I raise it so much that you are now at this point and going to go beyond. The moment you go beyond, you are going to jump from this negative magnetization to this positive magnetization, which would eventually decay to 0. So there is a finite jump in the magnetization, which is reminiscent of the system that we talked about for a first order transition, which was this Rx plus x cubed minus x5, where there was a jump in the magnetization as we crossed the point r equal to 0. Over here, there is a jump. If I were to start out near this, set my initial conditions near this negative branch over here, then it would happen that if I come close to the critical point, I would make a jump to the other branch, a finite jump, and therefore this looks like a first order, somewhat like a first order transition. So introducing a little bit of magnetic field can make the transition look like the second order nature of the transition is gone. It is more like a first order transition if either you don't see anything, you don't see the critical point at all, you just stay on this curve, go up and go down, you can do that. Or if you were to start over here, your initial conditions over here, there would be a jump and then go down. So there could be a first order like transition if I put this system in a magnetic field and change the temperature. So therein lies the sort of sensitivity of this Pitchfork bifurcation to external parameters having this epsilon, or in the second order transition language, having an external magnetic field completely destroys the nature of the bifurcation. So once again related to the point that x equal to 0, which was always a fixed point of the unperturbed system, ceases to be a fixed point as soon as you have an infinitesimal condition. Yeah, go ahead.
Sir, this coefficient of x cube, which is minus 1 here, so 0, so is necessary to be minus 1? The coefficient of x cube, Rx minus x cube.
I'm talking about the forward bifurcation, which would certainly require minus sign over here. If I were to talk about the plus sign, then the bifurcation, would look like.
No, sir. What I meant is, can it be minus 2x cube or something like that?
Oh, certainly I can just scale it out, right? I mean, yeah. X dot equal to, say, let's say Rx minus alpha x cubed, say set x equal to beta y, then beta y dot is equal to R beta y minus alpha beta cubed y cubed. So y dot is equal to Ry minus alpha beta square y cubed. And now, I mean, the beta is an arbitrary factor. I just take alpha beta square equal to 1, and therefore it is always possible.
Sir, by introducing this epsilon, means for the magnetization test, we introduced a magnetic field that will break the isotropy of the system, right? Will have a preferred direction.
What was the last part about by introducing the epsilon?
Means I'm breaking the isotropy of the system, like I'm giving a preferred
You are
direction.
breaking the up-down symmetry over here.
Yes.
Yeah.
So this property that the second order phase transition will be lost and we will have a fast order like phase transition. That is a general property if we introduce any.
Symmetry breaking perturbation. So, is this, I mean, could I have the last bit on this issue would be, could I have written down the fixed points over here? That is this y cubed, I have to solve for x star cube minus, so that's something that is worth knowing, that this is something that could have been, could have saved myself the pictures and the drawings if I just did y cubed minus r y minus epsilon equal to 0, to write y equal to cube root of p plus cube root of q, then y cubed is equal to p plus q plus 3 cube root of pq times y. So y cubed minus 3 cube root of pq y minus p plus q equal to 0, which tells you that p plus q is equal to epsilon, and 3 times pq to the power 1/3 is equal to r. So pq is equal to r cubed by 27. So p minus q is epsilon square, p plus q whole square minus 4pq. So 4r cubed over 27 square root of that. So you get your p and q as p equal to epsilon 2p equal to epsilon plus square root of epsilon square minus 4r cubed by 27, and 2q equal to epsilon minus epsilon square minus 4r square over 27. So I'll now take p to the power 1/3 plus q to the power 1/3, and you have got your y. So these solutions can actually be written down quite trivially. You can see what has emerged is this curve over here, epsilon square. There is the square root over here would be changing sign at epsilon square equal to 4r square over 27, which is epsilon equal to 2 by 3 root 3 r to the power 2 by 3. So that's the curve that I had over here. So this is my critical curve. If you are above this critical epsilon, if this chap over here is going to be positive, then there is no question of having more than one real root. So real roots, you can have only one of them if your this discriminant is going to be positive. It is only when things become interesting, only when the discriminant becomes negative and p and q become complex numbers. It's only when p and q are complex and could be put in the form r e to the power I theta, and q similarly some r e to the power minus I theta, that you start generating these solutions which differ in phase by e to the power 2 pi I by 3 and 4 pi I by 3. So those are the three real roots of the cubic, and that corresponds to this 3 fixed point part of the phase diagram that I have over there. So the 3 real roots of the cubic equation over here correspond to the 3 fixed points over here. Outside, it's just 1 fixed point, and the curves are obtained trivially from the discriminant over here. So if you know how to work with cubics, all this can be short-circuited, but But if you don't know, I mean, all right, I mean, if this were to be the fourth order, you can still handle, but much more problematic. Fifth onwards, you can't do it. So it makes sense to go through the diagrammatic procedure, that at least that always is there, and you can still get a lot of information out of it. So all right, and two of these down, I need to go to the third. So two of them down, both having the same fate, put a little bit of perturbation, out go the transitions, very susceptible to perturbations. X dot equal to r plus epsilon minus x squared. Nothing happens. X star is plus minus square root of r plus epsilon. So long as epsilon is small and does not create a real nuisance by becoming, I mean, it's a sort of, a negative epsilon and making the whole business problematic for you. But epsilon positive and small, epsilon positive, you don't have a difficulty. You still have two fixed points, and they would have to merge. I mean, these two fixed points are not going to merge at r equal to 0, but they are going to merge at r equal to minus epsilon. So a picture that I had of this tangent bifurcation for epsilon equal to 0 would, for epsilon greater than 0, simply become a picture which looks like this. It's just that the point at which the bifurcation has happened has changed. It is still the same kind of bifurcation. Two fixed points, bifurcation was gone. With epsilon equal to 0 in those cases, there was a transition from one solution curve to another solution curve. Over here, you find, and when you put an epsilon, the transition just didn't happen. You remained on one solution curve forever. Over here, the bifurcation is that two fixed points which are sort of part of the same solution curve, and x equal to plus minus square root of r, they come and merge and disappear. Here also you put epsilon perturbation to it, they come and merge and disappear, and therefore this to a small epsilon, this does not, for addition of a small epsilon, this doesn't change. The nature of the bifurcation does not change. That is why you would find that these bifurcations are called structurally stable. So the tangent bifurcation is structurally stable, whereas this chap over here is structurally unstable. Both the transcritical and the pitchfork structurally unstable. The tangent bifurcation is structurally stable, and consequently this does have a much larger role to play, especially when the dynamical system turns out to be of a higher dimension, and the tangent bifurcation becomes what's called a saddle node bifurcation, as we'll see in a week. the structural stability of this kind of a bifurcation makes life sort of easy when you have found something for some parameter range and then want to argue that it would still happen if things changed a little bit. That's the kind of thing which does not happen for these transcritical or Pitchfork, and that's what makes problem for the they exist in nature. These things can, I mean, you models bifurcation. There are bifurcations which are of the Pitchfork variety in nature, the second order phase transition, for example. But they do depend on tuning parameters carefully. In the second order phase transition, you have to tune the external magnetic field to be exactly zero in order to see the second order nature of the transition. So this question of tuning parameters to see the bifurcation becomes very important if it is transcritical or Pitchfork. It is, on the other hand, small changes in parameters keep the canyon bifurcation unaltered. So there is some, there is certainly a difference between these two classes of bifurcation, and there is some merit in of stability. That is, I mean, being confident about a system which shows tangent bifurcation, you have more confidence that it would be stable against small variations in parameter. So that's it. So we'll stop here. Tomorrow I'll take up a particular example from population dynamics which Strogatz works out, and probably round it off with some general comments about bifurcations, which would essentially finish the purely one-dimensional systems. So that's